Hello everyone, I'm Stefan Tabernig, and today I would like to talk about scalable transparent contacts for elimination of shading losses in solar cells. I would like to first thank the Photonic Materials Group and Dimitri Lammers at Amov, and also my supervisor Albert Polman, and also our collaborators at UNSW, who I worked together with on this project when I was visiting them. Now, to begin with, I'd like to remind you of shading losses. These are basically shading losses you get from bus bars and fingers at the front of your solar cell. And what's happening is basically that light that comes in is reflected by your metal front contact instead of generating carriers like you would actually want to. This will reduce the current and also lower the efficiency for your solar cell, and beyond that also leads to degradation because of the heat generation in your metal contacts. This is also especially an issue for concentrator solar cells, which usually have high metal front contact coverage of around 10%, and that's something we want to work on. And concentrator solar cells are interesting for us because the efficiency potential is well above that of non-concentrator solar cells. If you think about the current world record efficiency of 47.1%, this is 8% higher than its non-concentrating version, which is a significant amount. Furthermore, the fact that you concentrate light and hence need less active solar cell area means you use much less material than for non-concentrating cases, and that's relevant for 3-5 materials anyway, but also for silicon solar cells. Now, if you think that we really, if we follow through with our plan to really deploy silicon PV on a large scale to really generate a lot of energy in the future, then you really have to start thinking about what high purity silicon that we need for solar cells costs, and also the other materials that are part of the solar cell. And for this, it would also be in favor of basically having maybe a concentrator solar cell, which allows you to use much less material. At the same time, also silicon solar cells are more efficient by 1% than the current world record. So also from that perspective, it's interesting. However, there's an issue with concentrator solar cells, and that's the trade-off that you have between shading losses and resistive losses, which intrinsically hinders your efficiency gains. So what usually happens is that you have your solar cell, a certain efficiency at one sun concentration, and then if you concentrate more and more sunlight on it, your efficiency goes up. The efficiency goes up because you increase the quasi-Fermi level splitting in your cell, which gives you a higher VOC and hence a higher efficiency. But at one point, you basically level off and peak. And this is the point where your resistive losses start to take over because you have too much current in your front contacts. You could easily fix this by putting more front contacts on there, but then you will end up with generating less carriers in your solar cell, increasing the shading. And this conflict means they're kind of limited in efficiency around here for the world record at the moment. Whereas if you could fix this, you could follow this blue dash trajectory beyond 50%. And that's where we think we would like to go. We would like to be able to concentrate more sunlight without having to pay this penalty of resistive losses. How do you do this? We propose to use elimination to eliminate this trade-off towards 1000 suns by using refractive V-grooves. So the idea is that you have V-grooves on top printed into a polymer that's on top of your solar cell that refracts light away from your metal contacts onto your absorber material. Our intention is to make this with substrate conformal imprint lithography, which is a scalable approach and uses the 5 steps mentioned down here. So you have your silicon wafer, which will be your master. You pattern it. In our case, we used KOH patterning, and then you pour PDMS on top of it. You let it cure and then peel it off, and then you have your PDMS stamp, which you can use to pattern your samples. And that's what you do in step 4, which is the crucial part. So you have your solar cell with the metal contacts on it, and then you spin coat, in our case, Ormocomp on top of your solar cell, and print or push the PDMS stamp into it. The features of the PDMS stamp then you align with your metal contacts, and after UV exposure, you end up with your final solar cell, which looks like this. I'll spare you the details to the fabrication. I'll just show you some more characterization of the samples. And if you do this, first of all, you can do an SEM crosscut to see if what you designed is really what you have. And what you see here is basically here the ormocomp, then here down here your substrate, and here your metal contacts. And above the metal contacts, you can see a V-groove. So you have a nice correspondence between design and fabrication. And optically, it also does what you want. So down here you see an optical microscope image of your structure. And you see loads of lines here, which are a bit darker, and that's basically metal contacts with V-grooves on top. And if you look closely, you can see, because in our case we have gold and silicon, that what you see in the optical microscope doesn't look at all gold, but just grayish, which is the silicon that you can see through the V-grooves, implying that your gold contacts have become invisible. Just as a proof that there's actually gold contacts under here, I also looked for an air bubble defect where you can see that actually you really have gold under it. You just don't see it in all the other regions. So this is like a first step towards quantification. To be a bit more quantitative, now we looked at reflection. So what we did is we fabricated our gold contacts on quartz substrates, because that allows you to do reflection and potentially transmission measurements, and then looked at how the reflection changes for your pattern sample. So we have one reference that is just quartz, which is the ideal reference. We would like to perform like this. And then we have also a reference which is with a flat ormocomp layer on top of contacts on top of quartz, which basically doesn't contain the V-grooves. We don't want to perform like this because this means you can see the gold. So then the range you want to look at in our case is between 700 and 800 nanometers, because that's where gold is highly reflective and you don't have any parasitic absorption. And if you do this, you see that our pattern structure performs very much alike the quartz substrate, which implies that we have achieved high transparency. And in fact, if you quantify this difference, then you have a transparency of 95.2%. This is nice, but also for concentrated solar cells, you have to think about what happens if you come in at non-planar, not straight incidence, but say at under an angle. Because if you concentrate light onto your solar cell, you will come in at a range of angles, and that's what we analyzed in a second step. Again, we used the same sample, but then basically looked at the performance under angles. So what we did is basically we had the sample, light was coming in from the perspective of the viewer, and then we rotated it along the axis that's parallel to the V-grooves. And the idea is that if you rotate it more and more and more, then the V-grooves work worse and worse and worse, and you start to see the gold. You can peek in under the V-grooves to see the gold again. And in this case, we wanted to see, okay, this would mean that the parasitic absorption of the gold should go up, and for this, the best range to quantify this is between 350 and 500 nanometers. And you see that basically from ideal performance at 0 degree, you really have more and more parasitic absorption if you go to 30 degrees of angle of incidence. And if you take a slice through here, you can basically plot your your quality of your transparency as a function of angle, and you see that it's best at 0, and then at 20 degrees you already level off and have lost all transparency. So we're strongly dependent on theta. But there's a second angle, phi, and that's basically the angle that corresponds to rotation along an axis normal to your V-grooves. And in this case, we don't expect a lot to happen, because your V-grooves orientation towards light doesn't really change, so the function should still be given. At one point, at the Brewster angle of 57 degrees, you expect more reflection from because you're beyond the Brewster angle, but apart from that, nothing much should happen. And if you do this, then you really find that that's the case. So your parasitic absorption doesn't go up at all, and we can conclude that we're independent of phi. Now this is nice. Those two realizations will later on allow us to basically look into how we can shape the concentration onto our solar cell to basically have the least amount of losses possible. But before that, I just want to quickly show you that we can also we've also fabricated cells and have electronic data. And what we're looking at here is basically the EQE for a silicon solar cell with a silicon nitride AR coating at the front. pyramidal texture, and 25% metal coverage. So this basically means you have a lot of metal coverage at the front and gives you 30 milliamps in current, and corresponds to the blue line here. So what we did then is basically we deposited Ormocomp and looked first what happens if you deposit the planar layer, and then you get to this red curve here. And you have this increase because the pyramidal texture of your solar cell scatters sunlight into large angles, which are totally internally reflected by the Ormocomp layer. But the real gain that we wanted to see, and that we also see, is basically by adding the V grooves on top of our metal contacts. And you can see that we really regain our complete EQE up to a peak of 95%. And the remaining 5% are partially due to reflection from the Ormocomp itself, which we can't avoid in this case, and also due to fabrication defects like the air bubble that I showed you earlier. Now, knowing all this, we can make solar cells that work in the intended, that our V grooves work the way we want them to work, and we know the angular dependencies of these V grooves. Now we can construct a figure that tells us for what angles theta we can get what concentrations at what effective shading. The effective shading you can calculate knowing phi and theta, and with all these together, we can also calculate a potential efficiency gain, in this case for a gallium arsenide cell, according to detail balance. And just to give you an idea, those three curves here correspond to these three concentration patterns, where this one turns out to be the ideal one. So here we really let phi go all the way to the Brewster angle and make max use of that degree of freedom. And then actually we only have to go to a theta of 2 degrees to achieve 1000 suns, which was the goal. So at 2 degrees of theta, which is not a lot of loss when it comes to the angular dependence, we actually have just 0.6% of effective shading, which is really low, and potentially an efficiency gain of 5.3% according to detail balance. Now with this encouraging number, I would like to conclude and say that we demonstrated fabrication of this in a scalable manner. We completely regained the EQE after patterning with V grooves, and that we found a concentration pattern which basically would allow you to go to 100 to 1000 suns at 0.6% effective shading. And with this, I'd also like to say that now we're looking into applying this to highly efficient 3.5 cells as well. And just to give you an idea, a realistic like the perspective for a realistic gain would be, if you would take a gallium arsenide solar cell, that you gain 1.9% in efficiency beyond the current world record for concentrator solar cells. So we're really excited about that, and I hope I can show you more in the near future. Thanks for your attention.